Welcome back, students. So, today we will proceed our discussions on shear force diagrams and bending moment diagrams for a simple structures. The first simple structure we encounter in structural analysis is simply supported beam. Now, friends, all of us know what we mean by simply supported beam. We have seen it in our earlier discussions that a beam with one of the ends hinged and other ends roller is known as a simply supported beam. So let us assume that this is a simply supported beam of some length. Let us say the length of the beam. I will say the length of the beam is let us say 4 meters arbitrary, and it is loaded. Let's say this beam is loaded with a point load of 8 kilonewton and a uniformly distributed load of 3 kilonewton per meter. So these are the two loads that are acting on this particular simply supported beam. We'll name the ends of the beam. Let us say this end is A, this end is B. So we want to plot shear force diagram and bending moment diagram for simply supported beam. Remember, friends, these are all tools we are learning. Actually, our aim in this first unit is to plot axial force diagram, shear force diagram, and bending moment diagram for a portal frame or for a frame with inclined leg with or without internal hinges. Before that, we are learning the basic things in our structural analysis. So let us analyze this simply supported beam, which is loaded as shown in the figure. There is a point load of 8 kilonewton, which is acting at some point. Let us say I forgot to give this distance of this point load. Let us say distance of the point load from the left hand side is 1.5 meters. So naturally, the remaining distance will be 2.5 meters. We are taking odd figures over here, 2.5 meters and 1.5 meter. This is the distance of this point load from the left hand side and right hand side respectively from the ends A and B. We need to plot a shear force diagram and bending moment diagram for this simply supported beam. So friends, the first step in doing this is determination of reactions. How many reactions are there that we need to determine? So first step is determination of support reactions. So simple question, in our previous discussions we have seen that how many reactions are possible in case of hinged end. Determination of support reaction, this is the first step, and we can go further. We'll plot this once again. This is one of the ends that is hinged and other ends that is roller. In our previous discussions, during our previous lectures, we have seen that the hinge support will offer two reactions. This support will offer two reactions. So this support will offer two reactions. This is HA, I will say horizontal reaction at A. I will say this is vertical reaction at A. And this roller support will offer only one reaction, that is vertical reaction, that is perpendicular to the roller. I will name that reaction as HB. This is end A, this is end B. It is loaded with a UDL of 3 kilonewton per meter, 3 kilonewton per meter. And this 8 kilonewton load, point load, is acting at a distance of 1.5 meters from left hand side and 2.5 meters from right hand side. 1.5 meter on left hand side and 2.5 meters from right hand side. This is, let's call this point as C. Let's call this point as C. So we want to determine three reactions. Now the question is very clear. Our solution is very clear. There are three unknowns. Reactions are the unknowns. So there are three unknowns. So three unknown reactions are to be determined. Reactions are unknowns. So three unknown reactions are to be determined. And equilibrium equations, all of us know in two dimensions, there are three equilibrium equations. Basic, there are three equilibrium equations. Unless and until there is an internal hinge will provide additional equilibrium equation. So three unknowns and three equations. This means this structure is statically determinate structure. Last time we have seen what is the difference between determinate structure and indeterminate structure. And then ultimate aim is to analyze, our ultimate aim of this course is to analyze indeterminate structures. Okay, but let's start with the determinate structure. So three unknowns and three equilibrium equations. This means we can solve it without taking the help of any external method like moment distribution method, like slope deflection method, like flexibility method, like strain energy method, like stiffness method, whatever outside methods are there, they are all the methods to analyze indeterminate structures. Now here, three reactions, three unknowns, we can analyze using equations of equilibrium alone. So this is a determinate structure we can analyze. So let's write, the first step is over. Now the second step is to write the equations of equilibrium. So second step is applying equations of equilibrium to determine reaction. The second step, applying equilibrium equations to determine reactions. We don't need any extra equations. We don't need any extra outside method to determine reaction. Applying equilibrium equations to determine reactions. To determine reactions. So we are applying equilibrium equations to determine reactions. So applying equilibrium equations over here. So the first equilibrium equation is summation of forces in x direction is equal to 0. In two dimension, we know there are three equilibrium equation. Summation of forces in x direction is equal to 0. My assumption is all the forces acting towards right hand side I will consider as positive. Now these assumptions can be person specific. I will take the assumptions as right hand side positive x axis, upward y axis positive, and clockwise movements in xy plane as positive. There can be different sign conventions also, but these are my sign conventions. So I will start scanning the structure from A to B. We have seen the barcode scanner that scans from left to right or right to left. So I'm scanning the structure from left to right. I'm taking into consideration all the forces that are acting in x direction from A towards B. So let's start our scanning from A to B. So A, there is only one force HA acting in x direction. I'm talking about x direction forces. This VA is a force acting at A, but it is acting in y direction. So HA is the force that is acting in x direction, HA, and there is no other force acting in x direction throughout my structure if I go from A to B. Even if I go from A to B, there is no force acting from A to B. So I am writing the equation HA is the only force that is acting towards right, so that is considered to be positive, and there is no other force which is acting in x direction. So HA reaction is 0. That is my first equilibrium equation I have applied and got one of the answers. Now second equilibrium equation, summation of forces in y direction is equal to 0. Again my assumption is all the forces acting upwards are positive. I can take all the forces acting downwards as positive also, but since my experience says all the forces acting upwards are to be positive, that will give me a shortcut answer. That's why I have taken summation of forces in y direction is equal to 0. All the forces acting upwards positive. So we'll start from VA. We'll start from VA, so A to B and A to B. So we'll consider all the forces acting in y direction now. This is my x direction. Let me have the reference. This is my x direction. This is my y direction. And all the moments acting in xy plane, I'm considering clockwise moments positive. These are the moments acting in xy plane. Let me tell you, moments acting in xy plane are the moments about z axis. But let us consider M is the only symbol. Let's not consider MZ as the symbol. So I am starting VA. VA is the force acting upwards at A. So I am writing VA. I am writing it positive because it is acting in upward direction. My upward forces are positive. That is what my sign convention is. Then I will go from A to B. I will find this is 3 kilonewton per meter for 4 meters. So effectively 3 kilonewton per meter for 4 meters is the force 3 into 4. 3 kilonewton per meter for 4 meter. Effective load is 3 into 4, and this load is acting downwards. So I am writing VA minus 3 into 4. Why negative? Because this force is acting downwards, and my sign convention is upward forces I have considered positive. This means downward forces I have to consider as negative forces. So 3 into 4. Is there any other force? Yes, this is the force acting at point C. That is 8 kilonewton is the force which is acting downwards at C, downwards. So again, I am writing minus 8, that is the force VA, minus in 3 into 4 minus 8, and then VB at B. These are the only forces. VA, this 3 into 4 acting downwards, this 8 kilonewton acting downwards, and VB acting upwards. These are the only forces acting in y direction. So I am taking VB as positive because my assumption is positive upwards, and I have considered VB acting upwards. So that is equal to 0. So this is my equation, VA plus this 3 into 4 acting downwards plus this 8 acting downwards plus VB, that is equal to 0. Therefore, I will sum up the equation VA plus VB is equal to 3 into 4, 12 plus 8. If I take it on that side, that is 20. So VA plus VB is equal to 20. This is the result of applying second equation in this particular thing, at this particular structure. Now, my friends, I am applying the third equation, summation of moments acting in z direction, acting about z axis, that is acting in xy plane, is equal to 0. My sign convention is all the clockwise moments I will consider as positive. Now come back to this. The moment of HA at A is 0 because HA do not have any perpendicular distance with A. HA is passing through A. This reaction, horizontal reaction at A, is passing through A. It does not have any perpendicular distance. Moment is force into perpendicular distance. So if perpendicular distance is 0, moment also will be equal to 0. So HA into 0. This VA also same case. VA is passing through A point. There is no perpendicular distance between VA and A, and that is why VA into 0. So these two forces will not cause any moment at A. Since it's a first numerical, I am writing this. Next time onwards, one need not write this HA into 0. This is just for the understanding of the students. HA into 0 because there is no perpendicular distance. VA into 0. There is no perpendicular distance between VA and A. Now, the load is 3 into 4. 3 kilonewton per meter acting for 4 meters. Now this 3 into 4, 12 kilonewton meter load is supposed to be concentrated at the midpoint. At the midpoint, here it is supposed to be concentrated midpoint of the beam, which is at a distance of 2 meters from left hand side and 2 meters from right hand side. So this 3 into 4, that is 12 kilonewton load, is supposed to be concentrated at midpoint. So this 12 kilonewton load acting at 2 meter from A. And now if we consider how it is acting, it is we can say that this force is acting in a clockwise direction. This force is acting 2 into 4, 12 kilonewton meter acting at 2 meter. It is acting about A in a clockwise direction. So that clockwise moment is considered to be positive. So I am writing plus 3 is the load, 4 is the total distance, and 2 is the perpendicular distance of its effect. Okay, effective load 12 kilonewton. This is the effective load 12 kilonewton, which is acting at a distance 2 meters from left hand side and 2 meters from right hand side. This UDL is supposed to act at the center, so 2 meter. So in that case, 12 into 2, so that is positive because it is acting in clockwise direction. So 3 into 4 into 2 acting in a clockwise direction. Now next, this 8 kilonewton is the load which is acting at a distance 1.5 meter. This distance is 1.5 meter given. This distance of 8 kilonewton from A, it is given as 1.5 meters. So 8 into 1.5, that is also acting in a clockwise direction. This 8 into 1.5 will create a clockwise moment at point A. So plus 8 into 1.5. So I am writing plus 8 into 1.5 meters. Now, the last load on this, we have considered HA, we have considered VA, we have considered this UDL, we have considered this point load. Last one is the reaction VB, and the perpendicular distance of VB with A is 4 meters. And see, this VB will be acting in an anticlockwise. This VB will be creating an anticlockwise moment at A. So VB into 4, but that moment will be negative. So minus VB into 4, that is equal to 0. Therefore, this 3 into 4 into 2 plus 8 into 1.5, I will take VB on that side. So 4 VB is equal to 3 into 4 into 2, 3 into 4 into 2 plus plus 8 into 1.5, 8 into 1.5. Therefore, VB is equal to, I will cancel this 4 with this 4, and 4 twos are 8. So 3 twos are 6 and 2 1.5s are 3. So VB is 6 plus 3, that is equal to 9. Therefore, VB is equal to 9 kilonewton. That is the force I got. VB is equal to 9 kilonewton, 6 and 3, that is 9. Therefore, from the above equation, since VA plus VB is equal to 20, VA is equal to 11 kilonewton. That is how I got all the three unknown reactions by using equations of equilibrium alone. This is the determinate structure. VB is equal to 9 kilonewton, and therefore since VA plus VB is equal to 20, I got VV equal to 11 kilonewton. So I got all the three unknown equations. I am representing this reaction once again by drawing the diagram of the simply supported beam. I am representing these reactions over here. I have found all the three reactions. At A, two reactions, and at B, one reaction. A, B, two reactions, and this is 3 kilonewton per meter UDL, uniformly distributed load, and a point load of 8 kilonewton acting at a distance of 1.5 meter from A and naturally 2.5 meters from B. So this is 1.5 meter and 2.5 meter from B. So this is 8 kilonewton per meter. So I have just determined the reactions and I am representing these reactions, that this HA is equal to 0 kilonewton, this VA is equal to 11 kilonewton, and this VB is equal to 9 kilonewton. This is what I have seen, I have determined. So all the forces in this structure are determined, A, B, and this point, I have considered this point as C point. So A, B, C are the 3 points. Now, my friends, we are using method of sections for plotting SFD and BMD. Though this method seems to be somewhat lengthy